Let's revisit stoichiometry, utilizing the new method, the Rice method, for solving these types of problems. So we've got this question again, how many grams of nitrogen can be made from 9.05 grams of ammonia, reacting with 45.2 grams of copper 2 oxide. We're going to look for, first, what is the theoretical yield of nitrogen, and then in order to figure that out, we've got to figure out who's limiting. Then we're also going to look and see how much of the excess reactant remains. We'll disregard this third part, the percent yield, just because we covered that in the last one. But first thing we have to do is the first thing we have to do is convert these initial quantities of mass into moles by dividing by the molar mass. And when you do that, I get about, let's see, 0.531 moles of ammonia and 0.568 moles of copper 2 oxide. And if the reaction hasn't started yet, we are to assume we've got 0 nitrogen, 0 copper, and 0 water. Now, since the question isn't asking us anything about the copper or the water, we can just disregard that. That's just information that's not going to be utilized. And in our Rice method, this is the R, the reaction. This is the initial. The change, we can say, well, for every 2 ammonia we consume, we're going to consume 3 copper 2 oxide, and these come from our stoichiometric coefficients, to produce 1 nitrogen. Now, looking at this, we see we're going to use up 3 times the quantity of this copper 2 oxide because of that coefficient. So if X is anything, we're going to be consuming the copper 2 oxide, at a much greater rate than we will of the ammonia. And noting that the 2 ammonia and copper 2 oxide starting quantities are about equivalent, that suggests to me that the copper 2 oxide is going to be our limiting reactant. So now we can say, well, our ammonia, starting out with 0.531 mole minus 2x, and our copper 2 oxide is going to be 0.568 mole minus 3x, and then our nitrogen is going to be 0 plus x. Now, since copper 2 oxide is our limiting reactant, we set that equal to 0. Using that equation, you can solve for x, and you find that x is equal to 0.1893 mole. Alright, so now we can put that x into these 2 equations and solve for the quantity of ammonia that remains and the quantity of nitrogen that's produced. And the NH3 final is going to be 0.531 mole minus 2x, and x we put in as our 0.1893, and solve for that equation, and you come up with ammonia has 0.152 moles remaining, which is equivalent, when you multiply it by the molar mass, to 2.60 grams. The nitrogen is just 0 plus x, and our x, remember, is the 0.1893, and that is going to equal 0.1893 mole. Multiply that by the molar mass of nitrogen, and you should come up with something about like 5.31 grams. And this would be our theoretical yield, and this is the quantity of the excess reactant that remains. One more problem. We've got, what is the mass of lead 2 chloride? that can be produced when reacting 500 milliliters of our 0.150 molar potassium chloride with 150 milliliters of 0.150 molar lead 2 nitrate. Now, we can use the millimole thing, and just take volume in milliliters times concentration in molarity, and you come up with the quantity in millimole. So potassium chloride would be 75 millimole. Lead 2 nitrate would be 22.5 millimole. And our rice, this is our reaction, this is our initial, this is our change. So initially, we assume that the reaction has not yet started, so we've got 0 of either of these products, and one of the products we don't care about. We're asked to see how much lead 2 chloride can be produced. So we look at the stoichiometry and we see we're going to be minus 2x here, minus x here, because it is a 2 to 1 ratio, plus x here. And we see even if we consumed all of this 22.5 mole, minus 22.5, multiply that by 2 here, and it would still be less than the initial quantity of the potassium chloride. So that suggests that our lead 2 nitrate is our limiting reactant. So we can put these into our equations, and we come up with, for KCl, is going to be the 75 millimole that we started with, minus 2x. Lead 2 nitrate is going to be our 22.5 minus x, and our lead 2 chloride is going to equal the 0, because we didn't have any to start with, plus x. Now, since lead 2 nitrate is our limiting reactant, set that equal to 0, solve for x. X is equal to 22.5 millimole. Now, we can put that x into both of these equations. Here we solve for the quantity of KCl that remains, and here we solve for the theoretical yield of lead 2 chloride. And so lead 2 chloride, 0 plus 22.5 millimole x, lead 2 chloride is going to equal 22.5 millimole. Multiply that by the molar mass, and divide by 1,000 to convert to moles, and you come up with something like 6.26 grams of lead 2 chloride would be the theoretical yield. The KCl, put in the 2x, and you're going to be left with about 30 millimole, and just multiply by the molar mass, divide by 1,000, and you'll get its quantity that remains in grams. But because we weren't asked for that, it doesn't matter. If we were asked for what would be the final concentration of the potassium chloride, well, we could say there's 30 millimole of potassium chloride in our total volume, which is 500 milliliters plus 150 milliliters. And our total volume would be 650 milliliters. Millimole divided by milliliter gives us units of millimole per milliliter, which is equivalent to molarity, and I come up with 0.0462 molar would be our final potassium chloride concentration. That's just if that were asked for, another little bit of problem solving that we could do. Hope this works. Good luck.